Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about graph theory terminology, introducing the graph theory section in this OER, and this will be going into more depth in the graph theory basics video, and defining things a little more rigorously. So let's start with what a graph is. Let's start with a directed graph because that's actually easiest to define set theoretically. A directed graph can be thought of as a set of vertices V and an edge set E that's a subset of the Cartesian product V cross V, which it can actually be a multi-subset in general, but for a simple directed graph we can just think of it as a subset. So if the vertex set, say, is 1, 2, 3, we draw those as nodes 1, 2, and 3 as little dots on the page. And then if the edge set is, say, the set containing the pair 1, 2 and the pair 2, 3, the pair 1, 2 means we connect vertex 1 to vertex 2 in an ordered direction with a little arrow like that, directed from 1 to 2. And the directed edge from 2 to 3 is drawn here, so the direction just goes from the first element of the ordered pair to the second. An undirected graph is where you don't have these little arrows visually, but set theoretically we can think of it as saying our E, our edge set, is symmetric. So we have both the direction from 1 to 2 and the direction from 2 to 1, 1, 2 and 2, 1, and it will be important to think about the edges this way to do walks on graphs where we walk from one vertex to another. When it's undirected you can go in either direction. When it's directed you can only follow the direction of the edge. A simple graph is a graph with no self-loop edges, so no 3, 3 here that would make a little edge from 3 to 3, or V, V in general. And each edge has multiplicity 1, meaning we're not allowing it to be a multi-set if it's a simple graph. Each edge just occurs once. Most of the graphs that we deal with in this course will be simple graphs, but it's nice to know that we don't need that condition in general. Now, what about labeled versus unlabeled graphs? In the first graph theory video, we talked a little bit about graph isomorphism and how these two graphs are isomorphic because there's a bijection from the set of labels here to the set of labels there that preserves the edge set. So if I map 1 to 2 and 2 to 3 and 3 to 1, that's the relabeling that maps the first graph to the second and otherwise preserves the essential data of the graph. But as a labeled graph, these two are really different graphs. They're isomorphic, but they're different. And an unlabeled graph is an isomorphism class of all the different types of labelings possible on this graph, which means you just drop the labels and it's just the underlying structure of the graph. So that can be considered an isomorphism class of graphs. We will be dealing with both labeled and unlabeled graphs, but it does affect how you count things. There's only one path graph of length 3 if it's unlabeled, and there's a lot of different ways of labeling them if it is labeled. Now here's a complete graph. A complete graph on a vertex set V just means you have E equals V cross V, so all the possible edges are there, except for self-loops. We don't allow self-loops or multiple edges. So here's the example of the complete graph on 5 vertices, which we call K5, and of course you would say Kn for an n-element vertex set V. So here's 5 vertices, and all the possible edges between those 5 vertices are connected. Here's 2 other famous graphs. The path graph. P5 is the path graph with 5 vertices, just 5 vertices in a row connected by edges. You can also have 5 vertices in a cycle connected by edges cyclically. This is called the cycle graph C5. You can generalize this to Pn and Cn. Now, there's a special type of graph called a bipartite graph. This is not a specific class of graphs like Pn or Cn or Kn, but a graph is bipartite if you can split the vertices into a left set and a right set, so that all the edges go between the left and the right. And so you're not allowed to have an edge between 2 lefts, and you're not allowed to have an edge between 2 rights, and you can have some subset of the edges between the 2 sides. You don't have to have all the edges. But a complete bipartite graph is going to come up quite a lot, and it's where we do put all the edges between the left side and the right side. So we write Kn, M for the complete bipartite graph with n edges on the left, m edges on the right, and all possible edges in between them. In this picture we've drawn K4, 3 because there's 4 vertices on the left and 3 vertices on the right, and we've connected all of them. Now let's go back to the degree of a vertex of a graph. The degree is just the number of edges attached to it. So I've written the degrees here on each of these vertices of this pentagon plus a little edge. This vertex has degree 3 because there are 3 edges attached to it, and this one has degree 2 because there are only 2 edges attached to it. Now, a nice theorem is that the sum of the degrees of all vertices of any graph is twice the number of edges. In particular, it's even. So the sum of all the degrees, 3 plus 2 plus 3 plus 2 plus 2 in this case, why is that twice the number of edges? Well, if we think about how many times we've counted each edge, if I take this 3, I'm basically counting this edge and that edge and that edge. And then this 2 counts this edge and that edge. This 3 counts this one and this one and this one. This 2 counts this edge and that edge, and this 2 counts this edge and that edge. And if you notice, we've covered all edges exactly twice. That's because each edge has exactly 2 vertices that it's attached to. And so we count it once for the degree of the first vertex and once for the degree of the other vertex. And so the sum of all the degrees is twice the number of edges by counting in 2 ways, essentially. A subgraph of a graph is a graph formed by some subset of the vertices and a subset of the edges that stay within those vertices that you chose the subset of. So if I choose these 4 vertices that are yellow here and I don't choose the white vertex, then I'm not allowed to choose the edge that goes from the yellow one to the white one. That wouldn't be allowed to form a subgraph. But these 4 vertices, along with the 3 highlighted yellow edges, that's a subgraph of the big graph we have drawn here. The complement of a graph is formed by taking the vertex set to be exactly the same, but the edge set to be the opposite of what edges appear over here. And this is only defined really for a simple undirected graph. So if you have a simple undirected graph, no loops, no multiple edges, then you just have some subset of v cross v, and you take its complement in v cross v, and you notice the edges I've drawn over here are exactly the edges that don't occur on the left. So the complement of the graph on the left is the graph on the right. So now you try, put some of these concepts together by showing that the complement of the complete bipartite graph K43 is the union of 2 complete graphs. And that's all for today, and we'll see you next time.